Okay, a minute ago I stopped here at the point of trying to draw this because it's too hard to see the perspective on this crude drawing. So what I'm going to do is I'm going to assume that we do have a rotation. Just about the z-axis. So first, if omega equals ck, then rotation is about the z-axis. And the point at r equals xi plus yj plus zk does have velocity v equal to omega cross r, which is just c times x times k cross I equaling j, ck j, plus ck cross yj, okay, and that's actually then k cross j is negative x, okay, and that's minus cy I, and then it's ck cross k, which is 0. If we assume c is greater than 0, then we get something like this. View from above, from the positive z-axis, you're going to look down here, you're going to see your x and your y-axis. Okay, well, at a point out here, x and y are both positive, so you're going to have a negative cyi plus a ckj, again, assuming c is 0, and it's not ckj, it's cxj. Sorry if that was a distraction. Okay. ck cross xj, I, you get a c and x. And no reason to have an arrow over that x, if that's misleading. Again, I apologize. Okay, so anyhow, your negative, okay, your x and y are equal. And, you know, they're equal. And, but you have a negative yi, a negative cyi and a plus cxj, which gives you a vector in this direction. And of course, the bigger c is, that corresponds to faster rotation, the bigger this velocity vector is going to be. So here's your velocity vector. Now, if you just go around any circle, go over here, well, now your x is negative and your y is positive. So you're going to have a negative ji component, okay, because j is, y is positive, and a negative x component because y is negative. Same magnitude that you had here. You have this. And down here, you can check it out. You have this. You have this. And at the x-axis, your x is 0, sorry, your y is 0, your x has a positive value, so you're going to have a cx and j is going to be vertical. So you can take the axis intercepts and quickly see, and then it becomes very plausible and very easy to prove that this field is always tangent to any circle about the origin. Okay? And this helps you see why this is a model of rotational motion. If you go out to a greater distance, say twice as far from the origin, well, the x and y components are going to be twice as great. So the x and y will be twice as great. That means your velocity components will be twice as great. They'll still be equal and opposite at this point, so you're going to have a greater velocity out here. And all the way around the circle. And that just corresponds to the fact that if this thing is rotating at constant angular, that truck is not going to balance, constant angular velocity, then a domino close to the center is going to be moving more slowly than a domino twice as far out. Of course, different points in the domino are going to be moving at different velocities, and you get into the physics and the angular kinetic energies and angular momentum and so forth, and moments of inertia and all that stuff, which you've done. It's all totally related to rotational objects. I'm seriously thinking if we're going to do distance physics in the fall, of just doing everything with rotational objects. I can ship off a rotating, a rotational motion sensor. People check it out, either bring it back or buy us a new one, and do almost all physics with rotational objects. Okay, well, I'm getting off on a tangent there. But we can do just a huge chunk of physics by just studying rotational motion. Okay, you get the idea. So if this is an object, let's say this is just a system of two hoops. Okay, you got a hoop here and a hoop here. Okay. Obviously, this part of the hoop is moving faster than this part of the hoop, but it has the same angular velocity. It's just that the x, y, and z are bigger out here than they are here. Now I could go from there and develop a whole lot of physics. I do it every year. I'm not going to comment. It's not relevant to the calculus, but right there you have it. And this is also why I say that if you have an I and a j component to your omega, well, that just makes your rotation go about a different axis. And that's something that would be useful to prove. If you have an axis here, well, it still looks the same if you just look from out here along the axis. If you look back here, you see if the axis is in this direction, you see the thing rotating about that axis. So whoever carelessly wrote z-axis there must have been listening to my lectures or something, because I do a lot of careless stuff. And since this book was probably written before I could make any videos, I don't know how they managed to get polluted by my carelessness, and I was less careless back in those days. But nevertheless, something went awry, and I'm not knocking the book. I love the book. Little errors do occur. If this is an error, and if I happen to actually know what I'm talking about, and there's no guarantee of that, is there? Okay, so take it for what it's worth.